Hello everyone, we are Team 21 and this is our project for this term, Pneumonia Net. Pneumonia is an infection that affects our lungs and can be life-threatening. While it can affect any of us, one of the more vulnerable groups to pneumonia are children younger than 2 years old. The World Health Organization reported that pneumonia proves to be fatal for approximately 2 million children under 5 years old annually and has killed more children than HIV, malaria, and measles combined. When diagnosing, an X-ray scan of the chest area is often required. Our initial goal was to classify X-ray images as pneumonia or normal. However, this proved to be fairly simple, and so we modified our goal to classify the images as bacterial pneumonia, viral pneumonia, or normal. It is important to note that to achieve our goal of improving treatment time for pediatric pneumonia, our dataset consists of almost 6,000 chest X-ray images of patients who are aged 1 to 5. As such, our final model would not be helpful when diagnosing pneumonia for those older than 5.
The original dataset that our team obtained from Kaggle had two classes namely normal and pneumonia. Each image in pneumonia had viral or bacteria in its description. The data was pretty basic and needed cleaning and proper structure to be able to train our model efficiently. Originally, the data was split into test, train and valid but was highly disproportionate as evident. With only 18 images in validation dataset, model validation would have been very poor. Also, the total number of normal images were 1573, whereas the total mnemonic images were 4253. As you can see, the number of normal images is 1/3 of the number of mnemonic images, and this makes the dataset highly imbalanced. Imbalanced data, as we know, is a big problem as it makes the model biased and does not produce general results, and hence we needed to balance the data and resplit it. For milestone 1, we only implemented models to distinguish between pneumonic and normal lungs. However, after achieving a high accuracy for this distinction, we decided to further differentiate between the pneumonic images into viral and bacterial infections. As the first step in data processing, we removed all the grayscale and unsupported images. We wanted a standard size of 250 by 250 pixel for each image, with this being the average image size in the original data. Horizontal and vertical transforms are applied to augment the data and enhance the quality of our dataset. To solve the issue of imbalanced data, weighted random sampler, part of PyTorch data loader, was used as a sampler. The weights for each class were calculated as inverse of the number of data points in each class. Data was then shuffled and this sampler was passed as input to our data loader to balance the data across each class. After splitting the data into train, valid and test for two classes, the following were the data points across each class, and as evident, the data was fairly balanced and split of 80:10:10 for train, valid and test was used, which is a rule of thumb in data splitting. The data split for three classes is as shown, and it is evident the data is fairly balanced. This completed our data pre-processing, which is very important in machine learning since the model is only as good as the data.
Here is a high-level overview of the models we used, with the ones highlighted in green being our final models for each problem. As this was a classification problem, we used a logistic regression model with one dense layer as our baseline to compare against. When classifying images as pneumonia and normal, we implemented a convolutional neural network consisting of 3 convolutional layers with ReLU and max pooling after each. This was followed by 2 fully connected layers to perform classification. To further improve our model, we used transfer learning to implement an AlexNet architecture where we used 4 fully connected layers after the convolution to perform classification. After testing various hyperparameters, we used a batch size of 32, a learning rate of 0.001, and 10 epochs. With 3 classes, our models were similar, but we knew we needed to make things a bit more complex as we added another class. So, we modified our original CNN by adding one more convolutional layer, followed by ReLU and max pooling, and we modified our original AlexNet architecture by adding one convolutional layer and 2 fully connected layers after AlexNet's feature extraction. This was selected as our final model, and the same batch size was used, but we decreased our learning rate and used 20 epochs to train instead of 10 due to the additional class.
Next up, I'll be talking about the results. First, I'll talk about our two classes implementation. As you can see on the screen, there are two images. The left one is normal and the right one is pneumonia. Us humans without much medical expertise are able to distinguish between the good and bad lungs by looking at the debris or dust in the lungs. This is true for many images in the dataset. When we initially created our models to test between normal and pneumonia, we achieved really high accuracy. Our logistic had 91% and ANN classifier had 95%. These two images have never been tested on our model before, and so here's a short demo. So when we run our ANN classifier through these two images, it's able to correctly predict which is normal and which is pneumonia. When looking deeper into the fine print, the confusion matrix also yielded excellent results. The challenge came when trying to distinguish whether a pair of lungs with pneumonia had a bacterial or viral infection. The image on the left is clearly normal, as we're able to see. However, without much medical expertise, we cannot determine which is bacterial or which is viral for the images on the right. Doctors use a lot of information alongside X-ray images to also determine what type of infection a person has. Our attempt was to just use an X-ray image to classify the infection. We tried a variety of different models with different architectures. However, the one with the highest test data accuracy was our CNN classifier, which achieved an accuracy of 80%. These three images have never been tested on our model before, and here's a short demo. So when we run the CNN classifier through these three images, it's able to correctly identify which is bacterial, normal, and viral in nature. We wanted to know why our CNN wasn't achieving a higher accuracy, so we dove deeper into the numbers and looked at the confusion matrix. We saw high accuracies for all categories except when trying to predict normal images. When an image showed a normal pair of lungs, our model had a tough time predicting it and achieved a mere 53% accuracy. We wanted to know why it was so low, and so we manually went through all the test normal images. What we found was when the model was presented with a normal image, many times it thought this image was bacterial in nature. And so we went through the bacterial images and compared them with the normal images that weren't classified correctly. To the human eye, they look very similar. Here's a demonstration of our model failing to accurately classify these images.
So for the CNN classifier, when we pass our normal image, it actually predicts that it's bacterial, when in fact it was normal, and this occurred many times. We also compared our ANN classifier for 3 classes against the CNN classifier for 3 classes. And when we compared the confusion matrices, we found that the ANN classifier was able to predict the normal images with a 10% increase than the CNN classifier, from 53% to 63%, as well as many other accuracy percentages were up, even though the overall accuracy of the ANN classifier was slightly less than the CNN classifier. Moving on to the demo of our model of an ANN with an AlexNet for 2 classes. Here you can see that the model is run on unseen data and the accuracy is achieved for 95.23% when distinguishing between normal and mnemonic lungs. And now moving on to the next demo, which is a CNN with AlexNet for 3 classes, that is the normal lungs and the viral and the bacterially infected lungs. When this model is run on data it's never seen before, that is our new test data, we get an accuracy of 80.27% using the CNN. So the takeaways from this were that it's definitely worth spending time cleaning the data, and to save time, don't run the whole dataset at once, but test small subsets of training data. Rebalancing the data prevents overfitting and underfitting, and take note of any interesting insights to analyze later.